5.1 Part 1, Angle Measures. So we're going to first talk about angle measures in degrees. An angle is the joining of two rays at a vertex. So right here, where they meet, is the vertex. Angles are typically represented using a single Greek letter at the vertex. So for example, I would say we have an angle theta. So some definitions that might look familiar to you. The first one being complementary angles. They sum to 90 degrees. So if I drew a picture of that and it cut in the middle, I could have one that is 15 degrees and I could have another that's 75 degrees. Because when I add 15 and 75, I get 90. Supplementary angles add to give you 180 degrees. So that would look like this, where I could say my larger angle is 125 degrees and my smaller angle is 55, because together they add to give you 180. So acute angles are angles that are in between 0 degrees and 90 degrees, and I'm going to use this the Greek letter alpha just to represent acute angles. And then obtuse are from 90, and I'm going to use gamma, to 180. So if you have anything that is greater than 180 degrees, we call those reflex angles. Okay, so an angle in standard position, or it is in standard position when the vertex is at the origin, which it is right here, and one ray is on the positive side of the x-axis. So positive side on the x-axis. So this is in standard position. So again, we have to remember vertex is on the origin, and we have one of the rays is on the x-axis. And again, it has to be the positive side of the x-axis. So a positive angle is when we go counterclockwise. And therefore, we would go around like this. And a negative angle is when we would just go clockwise. And we would go in the other direction. So if you looked at the example we have over here to the left, this would be a positive angle because it's going counterclockwise. Something that you guys are all familiar with, a complete circular motion is one revolution, which is 360 degrees. So, knowing this, we are going to draw and label a few angles that are in standard position. So first off, for me to be in standard position, I need to have one ray on the x-axis on the positive side. So since I'm going positive, I can draw my ray anywhere else, but my angle needs to be going counterclockwise. So another example would look like this, and it's going counterclockwise, so we're going to call that beta. And then my last one, I can even make smaller, therefore acute. And again, it's in counterclockwise. So then to do a negative, we start the same position in standard form. And again, we draw the ray anywhere else, but we are going to now go clockwise. Another example, going clockwise. And one more example, going clockwise. So the word coterminal means that the two angles are going to have the same initial and terminal side. So they're going to start and end in the same place pretty much. So since we're dealing with angles, then we know one revolution is 360 degrees. So if I wanted to start right here on the x-axis, the only way to end there is if I went all the way around to 360 degrees. And since we just talked about positive and negative as far as the direction goes, that's why we have theta, our starting angle, and we can add 360 or we can subtract 360. So for number 3, I want a positive and a negative, and I'm going to give you a starting angle of 270. So that would mean if I wanted the positive one, I could take 270 and I would add 360 to it because it would give me a positive 475 degrees. So if I drew a picture of this, there's a couple ways you can do it. I start in standard position and I'm going to go in the positive direction, which is counterclockwise. So I usually go I go 270 degrees, which ends right there, but then I go around again 360, which ends at the same place where 270 would have ended. So for the negative coterminal angle, I would take 270 and I would subtract 360 and I'd get negative 90. So since this one, I usually, since it's the solution is going to be less than 360, we're not going to have like a continuous swirl, if you will, like we had in the positive one. We're just going to go negative 90 degrees. So the direction is going to be clockwise, so therefore that's all I can draw for negative 90. So for a positive angle or coterminal angle, if I start at 115, I'm going to add 360 to it, and I'm going to get 400. Oh, you know what? This one is 475. I misread on my paper. This one is 630. Sorry about that. And then for the negative, I would take 115 and I would subtract 360 and I would get negative 245 degrees. Something you might be wondering is if I gave you, let's say I gave you an example and I wanted you to start at 370 degrees and I wanted a negative one. Well, that means I would subtract 360. But when I do that, I'm left with positive 10 degrees. So I haven't yet found a negative coterminal angle. So what now I have to do is I can subtract 360 again, which will give me negative 350 degrees. So now I do have a negative coterminal angle. So we can keep adding and subtracting 360 degrees to any beginning degree, and we will end in the same position. So there's infinitely many coterminal angles to any beginning angle that is given. So some refresher with triangles. We know that triangles add to give you 180 degree, all their angles do. And then if you take the combined length of any two sides, that exceeds that of the third side. And then larger angles are opposite the larger side. Now, when we're talking with similar triangles, then the corresponding angles are going to be equal, and corresponding sides are going to be proportional. So now knowing all this, we are going to look at an example. Okay, so the question to this example is, how tall is the Washington Monument? Well, you need some information first, and I'm not going to write out the whole word problem, but I'm going to give you the scenario because I'm going to draw a picture for you. I also find that when you draw pictures and illustrate the problem given, it is much easier to visualize and see. I'm a very visual person, so if you're that same way, I highly recommend you do this. Okay, so I'm going to tell you that you are 67 inches tall. That's given. And at a given time, so a particular time of the day, the shadow of your shadow is 83.75 inches. So the sun hits down like this, but your shadow is on the ground. So your shadow is 83.75 inches. Again, information that's given to you. Now, for the Washington Monument, we don't know how tall it is. That's what we're trying to figure out. But at that same angle, at the same time of day, the sun hits it, creating a shadow that is 8,331.41 inches long. So, because it's the same day, and we're talking about the same shadow, the sun's in the same position, we now have two similar triangles. So, because we said corresponding sides are proportional, and that's what we have, two sides, we don't have angles, then we're going to set up a proportion. So to do this, there's a couple different ways you can set up the actual equation. As long as you're multiplying the same numbers I'm going to, then you'll get the same answer. So for similar triangles in this situation, then we know that for either situation, the height divided by the shadow length is the same. Okay, that's a fact because they are proportional. So knowing this, we can say, okay, well, if you are 67 inches tall and your shadow is 83.75 inches, well, that equals the height of the monument, which we don't know, over its shadow. So to solve, you're going to crisscross multiply, and h equals 6,665.13 inches tall. So that answers a question on how tall the Washington Monument is. The last part of this section that you need to remember and then therefore memorize deals with Pythagorean's theorem. So we know C is your hypotenuse, and then A and B are your two sides, and again, you can mix those up. It doesn't matter which one's which as long as C is your hypotenuse. And again, for this to be true, you have to have a right triangle. So when dealing with special right triangles, that we're going to start with 45, 45. So we know that this is 45 degrees and this is 45 because my right angle is 90 degrees. So because those two angles are the same, just like we said, the larger side is diagonal of the angle, same thing. So this 45 degree side is, let's say, diagonal to x, and so therefore this is going to be the same thing because it's diagonal and is the same angle, so therefore our two sides are the same. So because of this, we want to figure out what h is. Well, using Pythagorean's theorem, we would have x squared plus x squared equal to h squared. X squared plus x squared is 2x squares equal to h squared. And if I took the square root of both sides, I would be able to take out x because these would cancel, but the 2 would have to stay underneath. Same thing on h. The square root of h squared is h. So we have h equal to x times root 2. And this x right here is going to be the same x of our side lengths. Now for 30, 60, 90, let's say this is our 60 degree, this is our 30, and we know this is 90. Then we know that the smaller side is half of the hypotenuse. So if we proved it like we did before, we need to figure out what b is. So we have x squared plus b squared, which is equal to 4x squared, because I took the hypotenuse, 2x, and I squared it. Subtract x squared to both sides, you get b squared equals 3x squared. Take the square root, and b is x root 3. And this makes sense because 60 is greater than 30, which is diagonal to the b side, and if 30 has a length of x, then we're going to take that same x and multiply 3 to it, which makes it bigger, which is why it's the length of our 60-degree angle and not our 30. So yes, you can derive these, however, you need to memorize these relationships because you are going to use them very often.